So quite a few already know quite a bit about vertex algebras. And so if you look at the literature, usually this will be just called a vertex algebra. And then adding the O is by adding one more element to the data, namely a Virasoro vector. And often one also requires an integer grading. Well, just use the notation you prefer. But I want to point out that there exist vertex algebras that don't have a Virasoro vector and are still very interesting and also quite relevant. So it's well, anyway, it's just a name. So usually one requires a vertex algebra to have a Virasoro subalgebra. And to be integer graded or non-negative integer graded by some operator, which is usually called a Hamiltonian. So what does the Virasoro algebra means? There exists a vector called omega and called a Virasoro vector, such that the field corresponding to this vector omega, usually one calls it L of z, and one changes convention. One doesn't write here minus n minus 1, but minus 2. And one just does it because formulas are nicer. You could equally well write a minus 1. So the Virasoro Lie algebra is the Lie algebra generated by Ln, n running over the integers, together with a central element. The commutator is n minus m times Ln plus m, and then the central element. So here this is a central element, very much like the k in the affine case. Now, omega is a Virasoro vector if the corresponding fields, the modes obey these commutation relations for some complex number c. So that's then the number with which the central element acts. And then if it acts, we call it central charge. And this is then here called the Virasoro algebra at central charge C. Okay. Yeah, so usually one requires this, and let me give the example of an affine algebra, and then you see that it almost always has such a Virasoro element. So let's x1 1, I used upper indices, x1 up to xd be a basis of our Lie superalgebra G, and y1 up to yd a dual basis with respect to our bilinear form, which we now have to assume to be non-degenerate. And then one can write down the vector which is called the Sugawara vector. So S stands for Sugawara. I should also write down what I mean by dual. So by this I mean that just because the order is a potential sign difference. So then we have a special vector in our in this vacuum module of the affine Lie algebra, and it turns out that this vector normalized by k plus h check. K was this level of the Lie algebra, the level of the vertex algebra, the value with which the central element of the affine vertex algebra acts, and h check is the dual Coxeter number. So for example, for SLN, the dual Coxeter number is just n.
But is G a Lie algebra like it was before?
Yeah.
So the G is a Lie algebra like it was before, but what is the VUA?
Right. Yeah. So anyway, this is a Virasoro. It's a Virasoro field of central charge where the central charge is given by some expression in terms of k times the superdimension of G, the dimension of the even part minus the dimension of the odd part, divided by this k plus h check. So in particular, as long as we choose this level to be non-critical, not equal to minus h check, we always get a Virasoro algebra structure. Okay, I think I should define the affine vertex algebra.
Maybe not by erasing the definition of vertex.
Yes. So so let's see. We need to define the data. So our starting point is G to be a Lie superalgebra, B a bilinear form that is consistent, supersymmetric, and invariant, and a complex number k. And then this morning I have introduced this module for the affine Lie algebra, VKG. Right? Remember, this was the induced module, induced from the one-dimensional representation for the non-negative modes, where everything acts as 0 except the central element acts by multiplication with k, and then all negative modes acting freely. So in particular, this one has a PBW basis given by ordered monomials in some. Poincaré-Birkhoff bit.
I know what it stands for. What does it mean in this context?
Um,
As opposed to just talking a basis. What does it mean that it's a
The
PBW?
basis you get from the PBW theorem.
Yeah,
Yeah.
it was the ordering thing that he said about.
I understand what basis it is. I don't know what the word PBW basis means.
well, then it is a basis, and it's given in terms of these ordered monomials, and
But you're not asserting any property of it other than its basis.
yeah, no.
Okay.
It don't attach anything to PBW. It's a basis given by ordered monomials, and it's always called PBW. So we have this basis by ordered monomials, and now we have to think about it. The other data, we clearly have a vacuum vector.
Question. So this S that you defined lives in that V?
Yes.
Yeah, okay. And like even without talking about Vertex Operator Algebra, this forms a Virasoro field.
Yes, as long as I explain to you what the field is associated to this vector.
Okay.
Could you just put C is equal to 8K, what does it say? S?
It's K times the superdimension of G, right? So the superdimension of G is the difference of the even and dimension of the even and odd part. Okay, so then we need a translation operator. I will introduce this as the last thing. And we need a correspondence between fields. We need, in particular, this correspondence here, right? Okay, and
Sorry, it's a minor stuff. So I understood G hat was a super algebra via disparity, as you told us. How is the module a superspace? What is the parity inside that vector space?
right, we choose a homogeneous basis,
Yes?
and then this is an even element if there's an even number of odd elements appearing here and an odd element otherwise. Right, so it's just the parity is just multiplicative. Okay, so we have to understand what is the field associated to this one, and so let me maybe first give you a few examples. So the simplest example is,
So first of all, just to make sure I understand, V equals this VKG.
yes. So the fields corresponding to x negative 1 are the ones that already appeared quite often in this lecture. More generally, a field corresponding to just x negative m is a derivative, m minus first derivative of this field up to some normalization, which this example is a little bit lengthy, and I didn't copy it down, so I don't have this number in my head, but just a factorial. It's you can check it yourself. So there's a unique number here, a unique coefficient depending on m, so that this property is satisfied. Right? Check it, for example. In fact, here we checked it for, we computed the derivative here of x. Well, the derivative gives us a minus n plus 1 down. And now here the power becomes negative n minus 2. Now you can check, of course, if I insert n to be negative 1, we get a 0 here. So that coefficient doesn't contribute. If we take n to be negative 2, we get an x negative 2. Minus 2 plus 1 is minus 1, so we get a plus 1. So the leading term is x negative 2, 0 plus subleading terms. Right? Now take another derivative, a second derivative, we get another n plus 2. Right? So that means the terms for n equals negative 1 and n negative 2 vanish. And now if we insert n for n negative 3, we get minus 1 to the 2 factorial times this one, which actually answers my question. What?
I don't understand how that, how whatever you were discussing over there fixes a normalization here.
But, so let me first now write down the answer. It's 1 over m negative 1 factorial. Okay, so this is the field associated to this element. Okay, and now one can do the computation. One can the right-hand side. We know what it is. We can compute the derivative explicitly. We can let it act on the vacuum, and then write down the leading terms, and we will indeed observe that the leading coefficient, the constant coefficient, is the original vector. Right? Okay, and now one has to. What about the field corresponding to a vector like this? And AM and an NM. Yeah. Yeah. And the field corresponding to a monomial is an normally ordered product of the of the fields corresponding to the letters.
It's a true fact that this normally ordered product is associated.
And you have to introduce and you have to say that it's right nested or nested in one direction. In this case, it is right nested where. Is defined to be, sorry, another semicolon. You could also define it in the other. You just have to make a choice, and then iteratively. So this means you can introduce the notion of a field. Then one has to. The hard thing to prove here is this locality statement, which.
Is the thing you wrote defined? I thought you were only allowed to multiply them, and one has a z and one has a w. Well, no. So yes. So this is defined as endomorphisms on V exactly because of the property of this normal ordering, right? Because what you move to the right acts. I mean, it annihilates the vacuum. So this means two negative powers of a z will not appear because they eventually some mode will annihilate the given vector, and that makes the product S operators on V well defined. So, but this is a very valid question. But you could write what you're saying about which property the normal ordered product has.
Right. Right. So it's a. Okay. Let's do one thing. So this is how you introduce the fields for the affine vertex algebra, and then it is not hard but lengthy to prove that this locality property is satisfied, and then you almost have all properties
Of course, the field corresponding to the vacuum you just defined to be the identity. And the translation operator turns out to be given by the Virasoro zero mode. So that's how a whole vertex algebra comes in. And now, now you would like me to explain about the well-definedness of the normally ordered product, right?
Sorry, could you say what T is again in this case, in this example?
Yeah.
Translation is given by what?
So you define. So you set L to be the field corresponding to this omega defined here, to this one. And then it turns out you can define T to be the L naught. Yeah. So, and it turns out also at critical level you can have a T. It will then in that case just not come from the Virasoro algebra. Okay. I erase this, okay? Okay, now let's write down the formula for normally ordered product again. And now we want Z and W to coincide. And now let's write down what was A plus of Z and now let's act with the normally ordered product on a vector in our VOA. So I forgot the minus sign. Okay.
Well, you have to put down C in this case.
You're right.
And I guess one should only write such thing acting on a vector, right?
Hmm?
One should only write that acting on a vector.
Yeah, here the V is a vector.
So when you wrote it above, it's kind of...
Yeah, exactly. So you're always only, so it's always only well defined as endomorphisms on our vertex algebra. And that's important. So because what's happening now here, a negative, these are the positive modes. And if you think about it, the V is some normally ordered word in the negative modes. And eventually, if the modes become too positive, they will annihilate this vector. This is also called smoothness. So the property will here hold that for any given vector, A n V will be equal to 0 if n is too big, too positive. For fixed, so that means it's if n is greater or equal n for some fixed positive integer n, non-negative integer n depending on v. So what does this mean is the action of A negative truncates to a polynomial. Right? A polynomial.
B is still an infinite sum.
Hmm?
B is still an infinite sum.
And B is now still an infinite sum, but we have to think about what is the coefficient of a fixed power, right? And what's the coefficient of a fixed power. The same. So each coefficient for a given coefficient here. Again, it will happen that the Bn, if n is too positive, will annihilate it. It's a little bit tricky to see the details. The point is because of this smoothness condition, and that's maybe a good exercise to work this out. I can also prepare this for tomorrow. These expressions are still well defined as formal power series. This means the coefficient of any power of z is a finite sum of vectors in V. Okay, this is not obvious, and I actually didn't prepare this for this lecture, but yeah. Anyway.
So the smooth condition is always true, right?
The smoothness condition is always true, yeah. In fact, so somebody else asked that. So of course we have here now introduced vertex algebras coming from affine Lie algebras, and we will come to that one also has the notion of modules of a vertex algebra, and it will turn out that every module of a affine vertex algebra is especially a module of its underlying affine Lie algebra. The converse is not true. You have to require smoothness. So you are.
Why is the first term okay? Because there.
Yeah, and for the first term, right? I know only this, but here we have the same smoothness condition for B.
Yeah.
This means a Bn of acting on V is equal to 0 for n larger than a constant depending on B. So this means this action here is not a polynomial, but it's a Laurent series. And here now we are just acting with the A plus, and then if you think about it, it's really a tricky thing, and you ask a very good question. I just didn't prepare the answer, so I think this is in fact a really good exercise to check that this is well defined. And if you want, if anybody wants, we can discuss it after some lecture together. That exercise.
But it's just a fundamental thing that if you have a plus
yeah.
after or a minus in front, right, then because of this local impotency or smoothness, if you call it, then it follows.
Yeah. So
some elementary things about counting order.
Absolutely, it's a counting thing, and it's a good. So
wouldn't it also work if, as long as I apply on a vector, if I just take the product?
I mean, AB. Is that what you mean?
Yes.
Yeah. No, then they are infinite in both directions. And then the coefficients will be possibly infinite sums.
Yeah. Already with the example I raised with the Sugawara vector, you could nicely check that you would get infinite sums. It wouldn't work.
So just to check, like you're saying, this thing is true if A and B is smooth. Like this is well defined if A and B is smooth.
The action of the normally ordered product is well defined on any smooth module.
Oh, it's
yeah. So those of you who have read an elementary string theory book, so from the end of the 80s, one of the very first computation that comes there is to prove that the bosonic string only lives in dimension 26, right? And the bosonic string is coming from 26 free bosons. So free boson is just the vertex algebra associated to the trivial Lie algebra, the abelian Lie algebra C, and they have an ordering issue, which is exactly this ordering issue, and then they come up with a reordering prescription, which is exactly this normally ordering prescription. And one of the results that they get out of it is then that the Virasoro algebra that has this free boson theory has exactly the central charge 26. And then one goes on and observes that physical states can only exist if this central charge 26 condition applies.
This V,
Mm-hmm.
it's polynomials or power series? There's like an element of this V.
Mm-hmm.
Is it a finite sum of terms of this PBW basis, or is it a possibly infinite sum?
No, only finite sums.
Only finite sums.
Yes.
Okay, but then I don't understand why a.
No, it's formal power series in Z, where coefficients are finite sums of such monomials. Right? Of course, the power series that's an infinite sum, but each Z coefficients. Right? Now, a really good question. So we have a field acting on. So we have take two vectors. We act with a field corresponding to one vector on a second one. What do we have here? This is a formal power series in Z. So a priori, this is just a formal power series in V, but it becomes, because of the truncation condition, a formal Laurent series in Z. And so that means it's an infinite series, but coefficients are finite sums of such monomials. Yes?
Okay, so this example, so I hand you a Lie superalgebra by linear form, and this V equals K to make this. Which of these things that you defined are choices that you made, and which of these things are just, there was no choice, this is the only way that you could have done this? So you defined a lot of things.
So so here I have a huge amount of choices. For the conformal vectors, an enormous amount of choices. It is the accepted one, and it has the. But there's a choice.
What about for y of xm0? So the actual definition of the y, is that was there a choice there? Or
Yeah, this is a really good question. So I haven't seen a proof, but I'm quite confident that it's unique. But I have to think about it. So it's, I have to think about it. I'm pretty sure it's unique. Okay.
If you're at least willing to accept what T is, then I think that forces upon you everything else.
well, I thought that omega is
The T, and indeed that. Yeah. So you're asking. So I'm pretty sure that the answer is it's unique, but I don't know a proof at the moment. Yes.
So should this last line you wrote down, this Laurent series,
Mm-hmm.
be added to the list of axioms?
No. No, it should not.
Because this is stronger than what's in the axioms. This is not a consequence of your axioms.
Right. This is so. This is a consequence of if you impose a grading by non-negative integers. So you're absolutely. So I erased that you usually also define a non-negative integer grading on a vertex algebra, and given by a Hamiltonian, and you can use that property to also infer something like this. Anyway, yeah, you're right. The way I wrote it down, it's not part of it.
So we should add it. I mean, it should always hold. for whatever reason, that it should hold. That what you're saying, it should really be lower. When I apply it to a vector, I should not have infinite sums. So I should have infinite sums, but only to the right, not to the left.
Yeah, I would say there are so many variants of vertex algebras floating around. I gave you the minimal definition, and the minimal one I would take like this. Now and now you can put additional properties on it, and one additional property would be a certain grading that implies this condition. So,
which all the affine guys have.
The affine guys have this one. It's so it's a little bit problematic because there are so many variants of vertex algebras floating around. So I gave you the minimal one with which one can do a lot, right? Almost all of them have a zoo of additional good properties. One of them implying this statement. So this holds on. So let me write holds in most cases. Yeah. Okay. Good. Any more questions? Okay, then. Shall I stop here, or shall I give you a few examples? I started a little bit late, but what do you prefer?
5 or 10 minutes.
Yeah, it's maybe it's good if I give you a few examples because
we had a lot of discussion.
Yeah, which is really good. So it turns out every vertex algebra that one knows comes from an affine one of something like this via an iteration of standard constructions. Meaning in these lectures I have to tell you variants of various standard constructions, and then in principle you know everything one can get with the present knowledge. One kind of variant of this one are free field algebras. These are the simplest ones, and it's maybe a good thing to conclude with those. So they are usually they are divided into two types: free bosons and free fermions. And since I do things super, these are free super bosons and super fermions, and they.
Could I just make a remark?
Yeah.
Maybe that it might have sounded to some people when you motivated the normal ordering thing that one had to go to the literature and look in string theory and 26 dimensions and so on. But there is actually a fantastically good motivation for the normal ordering if you're just looking at the standard affine case and then looking at when, in order to make the action well defined, you led directly to the normal ordering, right?
Yeah, absolutely. And
so there is a sort of really math way of approaching
yeah, it's definitely reasonable that most of this could have or would have been discovered maybe a little bit slower without physics.
Yeah.
And the notion of a module for a vertex algebra very, very directly corresponds to the notion of a smooth module of the affine Lie algebra, meaning just that x times t to the n for n positive enough annihilates a given vector.
It might be good to go through and assume this tomorrow and then just prove that it's well defined the action or something, because it's a small argument, right?
I can think about it this year. Yeah.
That would calm down people maybe. You don't have to read string theory to understand.
Okay, so let me just give you two examples of VOAs. So what we do is we take a V to be a finite dimensional vectors. That's not a good name. What did I? Some letter I haven't used yet.
W.
W is better. A vector superspace, and you usually take it to be finite dimensional. No, that's the, and we take a B, a bilinear form on W, and then we can define the free superboson or superboson VOA associated to W. So it's usually denoted by a pi with an upper index W. And how do we do this? This W is a commutative Lie superalgebra. So actually, we have a Lie superalgebra. We have a bilinear form. So this means we can affinize it. So that means pi W is nothing but the affine vertex algebra, and the central element one usually takes to be one of the Lie, W as a Lie algebra with this bilinear form. So in fact, it was already included here.
So where V is supersymmetric and consistent, and it's automatically invariant.
Yeah, consistent. It's automatically, and B, indeed, I have to say it's a supersymmetric. Invariant is automatic, and it's yeah. So it's so this is really not a new example. It's just what's the simplest type of Lie algebra that we know is the commutative one. If I have a commutative Lie algebra, all I have to fix is the second piece of data. And of course, a bilinear form I can rescale as I like. So it doesn't really make sense here to put a level. I could equally well have put it in here. So that this is maybe the best notation for it. Now, if W is even, then this is called the Heisenberg or free boson. Heisenberg or free boson VOA of rank equal to the dimension of W. And in fact, an enormous amount of application just deals with the free boson. And if W is odd, then it's called the symplectic fermions. Yeah. And they are less known, but the symplectic fermions are in fact the simplest example of a logarithmic theory, that means of a vertex algebra with a non-semi-simple representation category. Okay, and
this is a new name for the same thing?
no, if W is odd,
No,
yeah, exactly.
Same construction as above?
Yeah, it's same construction, just the special cases. Right? The general construction is for any vector superspace. If the superspace is purely even or purely odd, it has a special name. Okay. And and one can vary this construction somehow to get symplectic bosons. Let me write this down as a last. And free fermions. So these symplectic fermions are not, if you look in the literature, often free fermions appear. They are different from the symplectic fermions, so not to be confused. And now what we do is we take again a vector superspace, and now I write it down as explicitly.
Could be neither even nor odd, right? It doesn't have to be one of those two.
Yeah, exactly. And in general, it's just a vector superspace. And all you need is an
supersymmetric bilinear form, and you get to this thing. Now, and so and V1, we want it to be even dimensional. And so here for this construction, I need to be a little bit explicit. And then one introduces a Lie algebra, G, which is the Lie algebra spanned by these where now here the indices are not integers, but 1/2 plus an integer.
What beta and gamma?
The beta and gamma, they denote a basis of the odd part.
What are you doing now?
I'm just defining another example of a vertex algebra. So it's the free field examples. And V was very badly chosen. I'm sorry, please make the V into a W, just because the V is always reserved for the VOA. So now, what's the underlying vector space? The VOA is our vector superspace spanned by normally ordered monomials in the negative modes here. Bless you. So as the vector space, we just take any words in the negative modes of these three. Very similar to the previous ones. And
Sorry, so G is the Lie algebras, the span of these, is that right?
yeah, right. G is sorry. First of all, yeah, we take G. We take G to be the Lie algebra of basis, these ones, and I forgot the commutation relations. So, and now we even though this is even, we declare the psi i's to be odd, and the beta and the gammas to be even. So really what we do is we reverse the parity here of this vector space. And it turns out if you reverse the parity, you can, it somehow naturally introduces this half integer grading. And now we define the commutator.
I cannot read. Is it N1 and N1?
Where are we?
No, psi I n comma beta a n.
These are commas. These are commas.
So these are not products.
No, this is just the list. It's just the list of the generators, and the commutator is just 1 if the indices if r prime is equal to -r and I is equal to j, and for the Yeah, it's so this finishes the definition of the Lie algebra, the underlying vector space, and now we have to see that what's the difference between this and this, right? This is also a vector superspace, and if I've changed the parity, I still have a vector superspace. So something must be different from this one, right? And the difference lies in this half-integer grading, which is reflected in that you define now fields. So for example, the field psi a of z, which is the field corresponding to the vector minus 1/2. Is now defined to be, well, I have to go over the correct modes, and here now instead of a 1, I have a minus 1/2. I want this to be integer graded, right? I can't write a minus 1 here. And similarly for the betas and gammas, so for example, the one for beta is defined completely in the same way. The point is, if you compute now the product, for example, of the product of psi a with psi a prime, and this is, if you still have energy, this is a very good exercise. It's very similar to what we did, but actually simpler. Then it turns out that this is, you get a first order pole here. While here, in this case, if you take now two elements, you take W and W prime and W, and then you then the corresponding fields are, I'll write it, W's always better. Somehow I have problems with a good notation. I write a tilde here so that we don't confuse it with a formal variable. Here we have a square. And you see, this makes sense, right? Fermions anti-commute. So if I change the order, well, of course I change the order of W and Z, and this gives me a minus sign here. Well, and bosons don't anti-commute. Well, if I change the order, I swap the order of the formal variables, but I square them, so I don't get an additional minus sign. Of course, you see a relation, namely, similarly here, the OPE of beta and will be of the same type, but now here if I change the order of the two, I would get a negative sign here, right? And this is why I have to change parity here, right? Because the bilinear form is supersymmetric, it's antisymmetric on the odd part, and I now need an antisymmetric, a symplectic form. That's why these are called symplectic boson, to define a consistent operator product on, I here forgot the normal ordered product, on these ones. Okay. Okay, I'm sorry. I actually went a lot over time. Let's stop here. These are the free field examples. So the one of them is just coming from a commutatively super algebra. But then what you should take out of it is there's a different variant that only has first order poles, which are called free fermions and symplectic bosons. Yeah. Any questions?
Should that also have a normal ordering? Should that also have a normal ordering?
Yes, they should also have a normal ordering.
Is this what people call BC systems? BC code systems?
Yes, these again pairs of free fermions. A pair of free fermions is often called a BC ghost system. So this yeah, exactly. So let me just say this in word. If W is purely even, then this is just called free fermions, or also BC ghost system. If W is purely odd, then this is called symplectic bosons or beta-gamma system. Beta-gamma now very suggestive. Or beta-gamma goes. It goes under these different names. That's, yeah. And it goes under the name of BC ghost because in the original string theory construction, one had to do a ghost fixing, a gauge fixing procedure, which you do by introducing a ghost and taking some cohomology, some BRST cohomology, and in fact it turned out you can only do this BRST cohomology if the central charge of the conformal field theory of the bosonic string is 26. The reason for this dimension 26.